When solving for a truss, I use a number of steps. First thing I do is I solve for my external forces. After I've done that, then I solve for my internal forces. So you can see in front of you, when I'm starting to solve for my external forces, first thing I'm going to do here is draw my free body diagram. I'm going to label all my reaction forces, and those are the ones that are going to happen at the supports, whether it's a pin support or a roller support. And keep in mind, a pin support is going to have two reaction forces, one in the X, one in the Y, where a roller support is going to have one reaction force, and that's going to act perpendicular to the surface. After I've done that, I'm going to go through and solve for a moment. So I do the sum of the moments equal to 0. Once I've solved for that, I'm going to solve for either sum of the forces in the X or sum of the forces in the Y direction. For the trusses that we're going to give our students, most of the time it doesn't really matter which one you start with, as long as you do the moment calculation first. Once I've done all of this, I can then use that information to go inside and start to solve for the forces that are on each internal member. Before I do that, I make sure I solve for all my unknown angles, draw free body diagrams of just one joint at a time, and then I'll solve for the sum of the forces in the X or the sum of the forces in the Y. And this one can matter, it depends on the joint. If you find that you hit a roadblock because you started with sum of the forces in the X, then flip and try sum of the forces in the Y and see if you can solve for that. Okay? So we're going to use the truss from problem 217, activity 217, and it's problem number 4. So we can see we have a pin support up top here, we have a roller support down here, and we have a 3-member truss with a 50-pound force pulling 3 feet from the wall. So it's a simple truss. We're going to end up having 3 reaction forces here. So we have 2, one in the X here, one in the Y, and then one in the X down here. Okay. So if we go back to those steps, we had here, draw my free body diagram, label the reaction forces. So right here I have the same truss drawn again, but I added in my reaction forces and I label them. It's really up to you how you name these things. It's not going to affect the answer in the end, but a lot of times it does help with your organization if you label them a certain way. So I have joints A, B, and C. I know that the roller support is going to have one reaction force. I know it has to act in the X. So I'm going to say the reaction force at joint A in the X direction. Up top here I have joint B. And I know that we have 2 reaction forces because it's a pin support, one in the X, one in the Y. So I'm going to say reaction force at joint B in the X direction, as well as reaction force at joint B in the Y direction. Now, the direction that these forces are acting is important. And what I would say is, at first, if you're not sure which direction is acting, just guess. We'll find out in the end that if you guess incorrect, you'll get a negative answer, but it'll be of the same magnitude. So it'll tell you in the end that if you get, for example, a negative 50 here, you would end up having the correct magnitude of force, just the incorrect direction of force. All right, so we've drawn our free body diagram. Next step, we're going to do sum of the moments. And for the most part, the trusses that we're going to solve for, we're going to choose the pin support as my point of rotation. And if you remember back to our moment activity or back into the simple machines, a moment is equal to a force times a perpendicular distance. So if I choose joint B as my point of rotation, we're going to find out that the force of RFBY is 0 distance from joint B. So whatever the force of RFBY is, times 0 gives us 0 rotational force at joint B. The same thing holds true to RFBX. It is 0 distance from joint B. So therefore, it has a 0 rotational force. So these two forces here do not cause any type of rotation around joint B. So for the time being, we can pretend like they're not there. So then what we're going to do is look around the truss to see what other forces we do have. And I can see that I have RFAX. It's a distance away. And I have 50 pounds, which is also a distance away to our point of rotation. So I'm going to go ahead and start to label or start to set up my formula. So I'm going to say the sum of the moments at joint B equals 0. And I have the formula right here for a moment. A moment is equal to force times a perpendicular distance. So for every force that we have here times its distance, we have a moment, a rotational force. So the way that I choose to label these is I'll start off with the sum of the moments at joint B equals 0, 0 equals, and I'm going to label moment, M for moment, and then whichever force is causing that moment. So M RFAX, that helps me to know which one I'm referring to, and then plus M50. Now when we're looking at whether it's a positive or negative rotational force, we're going to say that the counterclockwise rotation causes a positive moment, whereas the clockwise rotation causes a negative moment. So notice how if you held joint B here and you were to push here, it would cause counterclockwise rotation. Whereas if I pulled down on 50 here, it would want this truss to go this direction, clockwise. So I applied the negative 50, negative moment for the 50-pound force. So as I start to move down the formula, I added 50 to the moment 50 to the other side. I broke the moment into its force times perpendicular distance. So the 50 pounds is 3 feet. Remember, it's a perpendicular distance. A lot of times people want to go this direction, but we have to think about how far perpendicular is it. So I have 50 pounds times 3 feet equals RFAX times 3 feet. When I go through and do the math, I get 50 times 3 divided by 3 equals RFX times 3 divided by 3. So I'm going to cancel out the 3's on this side, cancel out the 3's on this side. I end up getting RFAX equals 3. So at this point, what I would do is then take my answer and I would put it in my free body diagram. Since I got a positive magnitude of force here, that means I assumed the correct direction of force. All right, now that we've solved for RFAX, we can use that information in order to solve for RFBX, and then eventually go around and solve for RFBY. So what I'll do next is say the sum of the forces in the x direction equals 0. We have RFAX, which is here. We have RFBX, which is here. Since we solve for RFAX and know that it goes to the right, we know that every action has to have an equal and opposite reaction. So if I'm pushing to the right, something has to be pulling back to the left in order for it to be balanced out to be equal to 0. So therefore, RFBX has to be going to the left, so it's a negative force. So what I'm going to do is go ahead and apply my knowns. I get RFBX is equal to RFAX. RFBX is equal to 50 pounds. I'll go ahead and add that information into my free body diagram. Next, I'll solve for the y. Sum of the force in the y direction equals 0. We have two y forces, RFBY, and the 50 pounds. Since the 50 pounds is acting in the negative y direction, we're going to apply it as a negative force. I'm going to add 50 pounds to the other side and get that RFBY is equal to 50 pounds. Again, I'm going to go ahead and add that to my free body diagram. Now that we've gone through and solved for all of our external forces, we're going to go inside and solve for our internal forces. So if you remember the steps that we showed you before, what I'm going to do here first is solve for my unknown angles, draw my free body diagram now of just one joint at a time, and then solve for your x and y components. So if we look over here at the truss, we can see that my y component is 3 feet, my x component is 3 feet. And if you know anything about trig, or simple triangles, we know that if the x and y components of a triangle are equal length, that means that the angles have to also be equal. So we have 45-degree angle here and a 45-degree angle here. If these sides weren't the same distance, we would have to go through and use our trig, sine, cosine, or tangent in order to solve for what our angles are. Now that we've solved for our unknown angles, I'm going to go ahead and draw a free body diagram of one joint. I chose to do joint A. For me, joint A had the least amount of members or forces on it, so it was a logical decision. When you're drawing the free body diagram of the joint, we'll draw the letter, put a circle around it, and then apply any forces or members that are physically touching that joint. The forces that are out here are not going to be included on this. I know that my force RFAX is going to the right, and I only have one other X force, so therefore it has to oppose it, so AC is going to go to the left. Again, if you're not sure, just guess, and in the end you'll get the correct magnitude, just a negative answer stating that you guessed the wrong direction. So I'm going to go ahead and solve for forces in the Y, forces in the X. So I'm going to start off in the Y direction. Sum of the forces in the Y direction equals 0. 0 equals AB. Notice that there are no other Y forces here. So if there aren't any other Y forces, and we know that the sum of the forces in the Y direction have to equal 0, therefore AB has to be equal to 0. Sum of the forces in the X direction equals 0. 0 equals RFAX plus a negative AC. We know RFX is positive because it's going to the right. AC is being applied as a negative force because it's going to the left. Add AC to the other side. AC is equal to 50 pounds. For joint C, we're going to go ahead and draw all of my members and forces that are affecting joint C. I know it's a little bit small, but take a look in here. What I did is, since this member is at an angle, we can't really use the formulas that we have, some of the forces in the X or some of the forces in the Y, in order to solve for that member at an angle. So we have to break it into its X and Y components. So I labeled it as BCX and BCY. Going to go ahead and solve for the Y component first. Sum of the forces in the Y direction equals 0. 0 equals. I'm going to go ahead and list all my Y forces. I have a negative 50 pounds since it's acting in a negative Y direction. And since I have one Y force going down and only one other Y force here, it has to go up. It has to go in the positive Y direction. So I'm going to go ahead and apply that to positive BCY. I'm going to go ahead then and say 50 pounds. I'm going to add 50 pounds to the other side. 50 pounds equals BCY. Now let's say I chose to go with the X first. And this way, in this problem, it wouldn't have mattered. So sum of the forces in the X direction equals 0. 0 equals, and we're going to go ahead and say 50 pounds, since we have the 50 pounds we solved for earlier, plus negative BCX. Since we know that AC is going to the right, that means that BCX has to go to the left. I'm going to go ahead and add BCX to the other side, and I get BCX equals 50. So this is good. We solved for BCY, we solved for BCX, but we still haven't solved for BC. And what we're just going to do is use our trig in order to solve for BC. So the sine of 45 equals BCY over BC. Sine of 45 equals 50 pounds over BC. Go ahead and rearrange, and we get BC is equal to 50 pounds divided by the sine of 45. And therefore we get BC to be equal to 70.71 pounds. And at this point, we've now solved for all of our members. We know that AB is equal to 0. We know that AC is equal to 50. And we know that BC is equal to 7.71 pounds. Now, there's one other thing I'd like to point out here. A lot of times, people will think that because this side is the same length as this side, that means that when we're solving for magnitude of force, this is the X and Y component to this member here. If we did that right now, 0 squared plus 50 squared equals our hypotenuse here, we're going to find out that we won't get the correct answer. So when we're looking at length of sides, it'll work out just fine. But when we're looking at magnitude of force, it's not going to work out.